Welcome to Math 31. This is a lesson on trig equations. So I'm going to be going through some problems that are basically like the 30 pure trig equations that you solve. So I'm going to review the method. Some of the questions will be a little bit, probably a little bit more complicated than the average ones in 30 pure, but of the type that you will encounter in this course. Now, to start off, let's not linger on really straightforward ones. But get right down to ones that require identity operations. So you're asked to find all values of theta in the domain between 0 and 2 pi. So this tells us first off that we're going to be in rads. And the questions we would assume to be as exact values unless they state otherwise. So I'm going to work all these ones out as exact values. And you'll be aware as well too that the domain includes 0 but does not include 2 pi. Now that's not always the case with the domains. You really got to watch them carefully because sometimes it goes 0 to pi, sometimes negative pi to positive pi. Bit of an irritation actually. But what I did is I had open in one end, closed in the other, simply because I don't want to, if I get an answer of 2 pi, I'll write it as 0, not as 2 pi. Small thing, but you want to be aware of it. First question. Cotangent squared theta plus cosecant theta is equal to cosecant squared theta plus 1. Missing a theta symbol there. Put that in. Now, typically with trig equations, if they involve more than one trig function, such as this one, you have to use identities to simplify them. And in this case, we have cotangent squared, cosecant squared, and also a straggler term of cosecant. So you check your formula sheet and see if there's an identity that links cotangent and cosecant. Specifically, one that links cotangent squared and cosecant squared. So keep your formula sheet in front of you always. And there is one. Now our choice is to convert cotangent squared into cosecant squared or cosecant squared into cotangent squared. Now ultimately both may work, but it makes more sense to convert cotangent squared into cosecant squared because then everything's in terms of cosecant. It's that straggler term cosecant that's the big thing. And I notice that the Pythagorean identity is the one to use. So we see that cotangent squared theta can be expressed as cosecant squared theta minus 1. And then carry everybody else down, plus cosecant theta is equal to cosecant squared theta plus 1. And then things start to happen. Those cosecant squareds cancel out actually. And we're left with cosecant theta. If we add the 1 on to the right side, they don't cancel, so be careful, is equal to 2. We do not deal with this in terms of cosecant, so we put it in terms of its reciprocal form. So sine theta is equal to the reciprocal of 2, which is 1 over 2. Now, the basic method for solving trig equations goes like this. You identify the quadrant that you're in. So for us, because sine is positive, it means we're going to be in quadrants 1 and quadrants 2. So on top of the axes is where sine is positive. And then we find the reference angle. Now to find the reference angle, we have a few choices. We do know that this is a special angle. This is sine. This is a ratio we should know. Sine theta is equal to 1/2. So we can do directly by going to pi over 6. So I use theta r for the reference angle. Now, the other method for it is on your calculator, and I don't necessarily recommend it, but it will work. And there are a few questions where you will have to. So if you're in degree mode, and the reason I'm suggesting degree mode is because if you're in rads, what will happen is if you get the angle, it'll give it to you in a decimalized version, not pi over 6, and then you'd have to fumble a little bit. So it's easier to do it in degrees with these. And anytime you're looking for an angle, you go second function of the ratio. So second sine 1 divided by 2, and you'll get the reference angle theta r is 30 degrees. Now, your reference angle is always a positive angle between 0 and 90. So it's never negative. And we, even if, as you'll see later on, even if the ratio is negative, we would ignore that and just key in the positive. Because all we want to do is get the reference angle in the appropriate quadrants. And then we find out what the principal angle is. So for this one, when we do know that we're in quadrant 1 and quadrant 2, we just roughly draw in the reference angle. The reference angle is always off the x-axis, above or below. So we have pi over 6 there, pi over 6 there. And it means that theta is equal to, in quadrant 1, is pi over 6. And then in quadrant 2, if you went all the way around, well, in degrees, it'd be easy to see it's 150 degrees. But in rads, we're comfortable now. It's 5 pi over 6. If you keep your unit circle around, then it shouldn't be a big problem. And there's our answers. Let's try a few more. Sine 2 theta plus cos theta is equal to 0. Same domain between 0 and 2 pi. When you look at this one, there's a problem first off because you've got sine and cos, two different trig ratios. Not good, because we would normally have to use identities to simplify them. But we also see the sine 2x. So we're thinking a double angle identity. Or I hope you're thinking that. If you take a look at your formula sheet, you'll see that this expands into 2 sine theta cos theta plus cos theta, let me call these x's, excuse me, plus cos x is equal to 0. Now, to solve this, you need to factor out a cos x from both terms. So cos x gets factored out, sits outside the brackets. Do not divide by cos x, because you're going to lose a solution with that. So if you do not divide by variables, only by numbers. And now we have 2 sine x plus 1 is equal to 0. Now when you set them to 0 to solve, you get cos x is equal to 0, and you'll get 2 sine x plus 1 is equal to 0. And we solve these both independently. So 2 sine x is equal to negative 1, and then sine x is equal to negative 1 over 2. Now we do the same thing as we did before. We identify the quadrants. Now sine is negative in quadrants 3 and quadrant 4. So if we were to go to this graph right here, where sine theta is equal to, back this one up, sorry about that. I'll go there in just a second. Let's get the reference angle first. That'll come in handy. The reference angle you will see again is equal to pi over 6. We saw that one a few minutes ago. But if you do use your calculator, go second sine, again 1 divided by 2. Do not use the negative. The negative is there just to tell you where to go, which quadrants you're in. It doesn't. You don't want to key in the negative, because then your calculator has to make the decision which one to give you, either the 1 and 3 or the 1 and 4. It'll give you the 1 and 3, but then it'll give you a negative answer. So it's much easier just to ignore it. Use the negative to tell you where you're at. So now I'll go to this, and up top I'll draw this. And here we have, I'm not drawing this to scale obviously, we have a pi over 6 reference angle there, then a pi over 6 reference angle there. So it means that theta, if you're in quadrant 3, your full rotation is going to be equal to 7 pi over 6. So easy to do it in degrees, but with the unit circle and with your own knowledge base in these, it's pretty easy as well to work strictly in rads. And then the other one, all the way in quadrant 4, is 11 pi over 6. Now below this, I'm going to work out the other one, which is cos x is equal to 0. And this is a quadrantal again. So when you see that cos and sine or the other ratios are equal to 0, you know you're going to be on one of the axes. And that's not a problem. But you do want to be careful, because what this is telling us is that our calculator may or may not give us the answer right away. So if you go second cos 0, it'll give you one answer. And there's going to be two answers, because if you think of the unit circle, the question really becomes, where is cos x equal to 0? And on the unit circle, I'm just going to really roughly sketch that. The 2 points where it's equal to 0 are up top and on the bottom. Because remember that cosine is associated with the x variable. So therefore, the answer is x, go directly there. X is equal to pi over 2, 90 degrees, and then 3 pi over 2, 270. So I didn't really need the grid that I was given, or that I made for myself. If you use your calculator, you can do that. But just be aware that your calculator will only give you the one answer, not the two. So you have to recognize, okay, I get 90 degrees or pi over 2. I have to then go after the next one, and using simple reasoning power. So we end up in this case with 4 answers. Let's move on to the next one. So the next question is secant. 2x plus secant x is equal to 0. This is a bit of a problem, or can be. Now we have choices with it, and typically with identity problems you can do things a little bit differently. Whatever, if you're algebra strong, you can bail yourself out of any problems. But what I'm going to do with this one is right away change this secant 2x into 1 over cos 2x. And then I'll change the other one to 1 over cos x is equal to 0. And then the next problem that we need to be aware of is that cos 2x. Now we have a choice, because some of you will take that cos 2x and correctly use a double angle formula on it and then solve it from there. And that's fine, because ultimately I'm going to have to do it. I'm going to wait. And the reason I'm going to wait is because whatever you do, you're going to have to get an LCD, because you're adding these two together. So the question is, do you get the LCD with cos 2x and cos x, or do you do it with a more complicated one? And I'm going to do it the way it is. And both will work. So our common denominator is going to be cosine of 2x multiplied by the cos of x. And it means the 1 over cos 2x we have to multiply by cos x. And then the second one we multiply by cos 2x. And this is equal to 0. And now we solve. Now I'm going to note that because of our denominators, cos 2x cannot equal 0, neither can cos x equal 0. So we have to be aware of that. There are restrictions. We might as well take care of those restrictions right away and then see if they come into play. So the restrictions would go like this. So cos x equals 0. Let's take care of this one, because we just saw this on the previous question. X cannot be equal to, pi over 2 and 3 pi over 2. We saw that earlier. And then the other one is cos 2x equal to 0. Now we can solve this one a number of ways. You can either use identities or you can use multiple angles. And what I'll do, just to be consistent with what's coming at us in a few minutes, I'll use a multiple or a double angle formula. And it doesn't really matter which version you use to simplify it, but if you go 2 cos squared x minus 1 is equal to 0, that's as good as any other. So we isolate the cos squared x. The sine, the other one would have worked fine too, and you get 1 over 2. And then cos x, when you take the square root, plus or minus 1 over root 2. So the root of 1 is 1. Now when you get this, keep in mind you're still solving what x cannot be, not yet what it is. When you go on with this, we see that the quadrants will be all. Cos is positive in 2 and negative in 2. And then you think about what the reference angle is. Now you could use your calculator, but I'll write this as xr. We do know that ratio, 1 over root 2. It's not rationalized like we often work with it, but it's going to be pi over 4. So it means that x would be equal to pi over 4 in quadrant 1, 3 pi over 4 in quadrant 2, 5 pi over 4 in quadrant 3, and 7 pi over 4 in quadrant 4 within the first rotation. So really what we're saying then is x cannot be any of those. So there's 6 numbers that are on the restricted list, and if x turns out to be any of those, we have to reject them. And now let's get on to the question. To set this one equal to 0, to solve for it, we care about the numerator. So really the question is cos x plus cos 2x is equal to 0. And here we use another identity with that double angle. And we have 3 versions of it. The one that makes the most sense to me is again the cos 2 cos squared x minus 1. That's because we have another cos term in it. So it will work better if we do that. So I'll write this, replace this, 2 cos squared x minus 1, and then of course plus cos x is equal to 0. And if we put this in descending order of degree, we'll get 2 cos squared x plus cos x minus 1 is equal to 0. And if we make a substitution, this is optional, but it will help us to see what's going on a little bit better. If we do make that substitution, 2a squared plus a minus 1 is equal to 0, you'll see that it's quadratic. And then we can factor this quadratic. So I'll bring up, I need a little more space to work with, but that's the one I'll work with. 2a squared plus a minus 1 is equal to 0. I think that's right. It does factor into 2a and a, 1 and 1, a plus 1, 2a minus 1. Check that out, but that should be correct. And then 2a plus 1 times, or 2a minus 1 multiplied by a plus 1 is equal to 0. This is turning into a fairly long question. So 2a minus 1 is equal to 0. A plus 1 is equal to 0. So a is equal to negative 1. A is equal to 1/2. I'll go directly to the answer. So the issue now is, or the question is now, cos x is equal to 1/2. Cos x is equal to negative 1. And cos x equal to 1/2 tells us that because cosine is positive, we're going to be in quadrants 1 and 4. They're all positive in 1, and cosine's positive in 4. Now you could use your calculator in degree mode particularly, so you could convert it. But we will get a reference angle of pi over 3. That's where cosine's equal to 1/2. So here we are with a pi over 3 reference angle in quadrant 1, pi over 3 reference angle in quadrant 4. So our answer in quadrant 1 is pi over 3. Our answer in quadrant 4 is 5 pi over 3. And then with cos x equal to negative 1, this is a quadrantal. You could use your calculator, or probably better the unit circle, because you think, well, where is cosine equal to negative 1 in the unit circle? And you will get x is equal to pi. So these are our answers. So there's 3 answers. We get to keep them because none of them are on the restricted list. Let's do one more, and we should be out of here. Now this one wants us to write our answer as a general solution. Previously, we had answers that were within one domain, or one rotation, 0, 2, pi. And now we're going to look at them as a general solution where you actually express your answer in a way that it doesn't fall within that one domain, but would cover infinite directions. And this also has a factor of 3 here, and you'll note that there is no triple angle identity, particularly for secant. So what we're going to do is solve this one as a multiple angle solution. So actually, I guess I didn't title that, but let me refer to it as a multiple angle. Now, there's a few things that you have to recall. And I haven't done a lot of review of graphing, although there is material posted. The period of y is equal to cos 3 theta is 2 pi over 3. Because normally it's pi, 2 pi, and then we divide by 3. Now this thing is squared, so possibly may change things. But let's see what we can do with it anyways. And therefore, the period of the reciprocal secant is also going to be 2 pi over 3. So now to solve this one algebraically, what we do is we make a substitution and pick a nice inoffensive variable, say a, and make it equal to 3 theta. Now some people don't bother with this. They don't make the substitution. They just reason their way through. That's fine too. Substitutions are usually done for you, just a way for you to see what's going on with it. But if we do make this substitution, then we get a better form because we get secant squared a minus 2 is equal to 0. And then when we solve, we get secant squared a is equal to 2. So we get secant a is equal to the square root of 2 plus or minus. And then for us, cosine of a is equal to plus or minus 1 over root 2. And this is what we want. Because this is a special angle, we know this one, we're going to be in all quadrants because it's plus and minus. The reference angle, AR, well, where is cos equal to 1 over root 2? That's 45 degrees, or pi over 4. So angle A would be equal to pi over 4 in quadrant 1, 3 pi over 4 in quadrant 2, 5 pi over 4 in quadrant 3, 7 pi over 4. So you could have drawn this in like that, each of the 4 quadrants. There's just one little problem before we wrap this one up. A is actually equal to 3 theta, and we're trying to solve for theta. So don't stop there. You need to note that 3 theta is equal to pi over 4. That 3 theta is equal to 3 pi over 4. That 3 theta is equal to 5 pi over 4. And that 3 theta is equal to 7 pi over 4. And then you solve for theta. And here's what we actually get. So dividing by 3 is pi over 4 divided by 3 is pi over 12. Divide by theta is equal to divide by 3, so you multiply by 1/3. And this one is actually going to give you pi over 4. Interesting. And then this one will give you theta is equal to 5 pi over 12. And then this one will give you 7 pi over 12. So those are our answers. Now, there are answers within one rotation. Now, we have to be aware, too, like I said, the period is 2 pi over 3. But any way you look at this, this is a horizontal stretch by a factor of 1/3. So when we try to write our answer in a general solution, we write it in such a way that we can note that those answers are recurring every cycle of the graph. So pi over 12, that one occurs on the next wave. Same thing with pi over 4 and 5 pi over 12. So if we take a look at the graph that I've got drawn conveniently for this one, we're finding out where, if you take a look at the original equation, where is this graph equal to 2? So here's what we have. We've got y is equal to, we had secant squared 3 theta minus 2 is equal to 0. This would be the same as secant squared 3 theta equal to 2. So if you broke this into two graphs, you have y1 is equal to secant squared 3x, y2 is equal to 2. So this, by the way, would be on your calculator. Y1 is equal to 1 divided by cos of 3x squared. And this is what you're going to get. And then really we want to know where this secant graph is equal to 2. And it would be right there. It would be right there. It would be right there. It would be right there, and so on. But you see that those curves, they keep on cycling. So we want to write these in such a way that we are able to generalize the solution. Now you can see that even though this isn't labeled, this does look like it's pi over 12, and it's, in fact, that's what it is. So this is 2 pi over 12. This is 3 pi over 12. This is 4 pi over 12. This is 5 pi over 12, and so on. So there is a regular pattern. 6 pi over, then 7 pi over 12. There is a pattern. And then the same thing is true in the negative direction. So what we can do is note that these ones occur. So theta is equal to, if we take the smallest one, pi over 12, you might note that the difference between them from 1 to 3 is 2 pi over 12. And then same thing here, 2 pi over 12. We're always going up by 2 pi over 12, which is pi over 6 if you reduce it. Same thing in the negative direction. So why not just write this as pi over 12 plus pi over 6, and then pick a variable like n. And by going n is an element of the set of integers, this simply means multiples of pi over 6. And then we have a general solution for it. So that tells anybody who's looking at this that that answer is going to keep recurring every pi over 6. Now you sometimes can't simplify it quite that easily because, you know, here what's happened, which is kind of unusual, is the distance from this point in the curve is the same there as this is to there. You would expect this to be the same because that's the same point on the wave. But you would not expect it to be necessarily the same distance from one in a different position. But that's how we work these ones. So I'm going to shut it down now, pause this, and give you a chance to practice some of these. But that's the idea with these trig equations. Not really the core of the unit, but they show up often enough that you want to make sure that you're on top of it. Thank you for your time.